Okay, folks. So today, the first thing we will be focused on is I am going to do one more acid-base neutralization reaction. But I'm going to do it with a weak acid, which is going to alter it slightly. Then we're going to talk about redox reactions. When I get into the redox reactions, I'm going to start with a bunch of definitions, and then we'll start applying those definitions. And that is the major goal for today. So, just as a reminder, you will have some other information. Number one, I will be in my office until 4 today after the class. My goal during that time, if all goes well, is to develop the answer keys for all of the homeworks that I have posted. And I may develop another homework, which is a mixture of all the types of calculation conversions that you will encounter. And that way you can practice spotting what to do. But that is number one goal. Number two goal is hopefully tomorrow. I plan to have your homework for Tuesday uploaded into Active. It will be over electrolytes, in the fact that you'll have to know your electrolytes in order to do precipitation reactions. It will be over acid-base neutralization reactions, complete ionic and net ionic equations. It will be over redox reactions. So it's going to be over a good chunk of what we have done this week, plus a little bit of what we did last week that's directly applicable to what we're doing this week. Also, and then on Tuesday, your active for the reactions lab is due. So you'll have 2 actives due on Tuesday. One will be a regular homework and one will be the reactions lab. Next week, my goal is to talk about thermochemistry during lectures on Tuesday and on Thursday. And your lab next week is going to be the gas law lab. The gas law lab itself is fairly fast, so I plan to do the gas law lecture before I turn you loose on the gas law lab. So you'll need to come prepared to take notes next week during the lab. If all goes well, next Thursday will be the last of the new information. Because you have a test, I believe, on the 22nd. I have to look, but I believe it's on the 22nd, which is the Tuesday, 2 weeks from, or a week from Tuesday. Will be your last, will be the 4th exam of the semester. So we are getting there. It's crunch time. I know it's not an easy crunch time, but it's crunch time. Questions? Okay, then we're gonna get started. So at the end of lecture on Tuesday, I introduced acid-base neutralization reactions. An acid-base neutralization, when we're dealing with an acid-base neutralization reaction, I'm going to focus on the Arrhenius definition of an acid, which is a proton donor, and the Arrhenius definition of a base, which is a hydroxide donor. When you combine a Arrhenius acid and an Arrhenius base, one of the products will be water, and the other product will be some salt. We talked about how to determine the state of matter. Acids will have the state of matter of aqueous. Your base will be determined according to the solubility rules. Water will be a pure liquid, and the salt will be determined according to the solubility rules. Now, if you have a strong acid and a strong base, the net ionic is easy. It's H plus OH minus supposed to form water. That is true for our strong acids and strong bases. However, if you have a weak acid and a strong base, or if you have a weak base and a strong acid, that will not be the story. So that is what I want to start with, is an example of a weak acid, strong base. And the weak acid I'm going to use is going to be the diprotic acid that you used in lab last week. I'm going to use oxalic acid. Oxalic acid reacts with sodium hydroxide. Again, this is an acid and this is a base. And you'll see that the definition for an acid is that it is a proton donor. The definition of a base is that it is a hydroxide donor. Because of that, that means that one of the products will be water, and we'll need to determine the other product. The other product will be a combination of sodium ion and oxalate ion. If you look at, and I will write bigger for the rest of this after I get the initial equation. I just now looked up. It looks big on my table, but not up there. Okay, so if you look at the ions that we're dealing with, we need to make this a charge neutral ionic compound. And so the charge neutral ionic compound will be Na2C2O4. And those are our two products. We determine the states of matter. Acids will be aqueous. Your base, you will be using your solubility rules. Since this contains a group 1 metal, it is soluble. Water will be a pure liquid. And with the salt, you use your solubility rules. Because this contains a group 1 metal, it is soluble. Now we balance our chemical equation. And to balance the chemical equation, you're going to need 2 sodium hydroxides and 2 waters. So this develops the balanced chemical equation. So what did we do in just this part? Number 1, we predicted the product. We determined this was an acid-base neutralization reaction because it worked with an Arrhenius acid and Arrhenius base. And since it's an acid-base neutralization reaction, that means one of the products is water and the other product is a salt. You got to be able to determine what that salt is. Well, that salt is going to be the cation of the base to the correct charge, plus the anion of the acid to the correct charge, and then you determine the ionic compounds formula by making the compound charge neutral. We then determine the state of matter. Acids are aqueous. Your bases you determine using your solubility rules. Water is a pure liquid. Your salt you determine using your solubility rules. And then we balance the equation. Any questions over that piece? Okay. Now is where you have to remember a very important fact. Well, I mean, I guess you have to always, but this is where students make their mistake. Going from the balanced chemical equation to the complete ionic. If you go back and look at when I discussed the complete ionic equation, the thing I said is you dissociate strong electrolytes. You have to, and strong electrolytes, you can't look at just strictly the state of matter, folks. Which is what students typically do. They go, oh, it's aqueous, it's strong. Nope. You got to go back to what is a strong electrolyte. A strong electrolyte is a soluble ionic compound. It is a strong acid, and it is a strong base. I say that because oxalic acid is a weak acid. And weak acids are weak electrolytes. How did I know oxalic acid was a weak acid? Anyone? It's not one of the strong acids. There are only 6 strong acids, folks. If it's not one of those, it's weak. Now, sodium hydroxide, being a soluble ionic compound, is a strong electrolyte. Water is a non-electrolyte. And sodium oxalate, being a soluble ionic compound, is a strong electrolyte. We have to know who the strong electrolytes are when we go to the complete ionic, because when we go to the complete ionic, the strong electrolytes are the only substances we break into ions. So this oxalic acid, it just comes straight down into the complete ionic equation. The sodium hydroxide, however, does get dissociated into its ions of 2 sodium ions and 2 hydroxide ions. The state of matter of the ions is the same as the parent compound. The coefficient of 2 in the balanced chemical equations means you have 2 sodium hydroxides. Meaning you have 2 sodiums and 2 hydroxides. This goes to make water, which is a pure liquid.
And then we have the strong electrolyte of sodium oxalate, which we are going to break into its ions of sodium ion and oxalate ion. The ions will have the same state of matter as the parent, but that 2 in the sodium oxalate, the 2 sodiums, becomes a coefficient because that 2 was strictly there to make that compound charge neutral. So this is the complete ionic equation. Now to go to the net ionic equation, you remove the spectators. Spectators are going to be ions that appear the same on the reactant side as they do on the product side. Everything else you bring down. And that, folks, is your net ionic equation for a weak acid. Strong base neutralization reaction. For oxalic acid. I'm going to say it one more time. You cannot assume that just because something is aqueous, that it is a strong electrolyte. That is the biggest mistake I see students make on acid-base neutralization reactions. You have to go back and actually pay attention to what it is to determine what type of electrolyte it is. Questions? Okay. We're on to the world of redox reactions. Redox stands for reduction, oxidation, reactions. Basically, redox reactions are reactions that involve a transfer of electrons. Examples will include single displacement reactions, It will include, synthesis reactions. Where two elements form a compound. It will also include, reactions of polyatomic ions where the ion is made or destroyed during the reaction. We can recognize a redox reaction by following
Unknown caller.
really the oxidation numbers or oxidation states of an element of elements in the reaction. The sheet of paper you were to pick up has the oxidation rules. And because this test is going to be a challenging exam, you're going, and partially because we had 2 weeks of snow, you're going to get your oxidation rules on the test. First time I've ever done that. So you'll get this on your test. Now, some definitions. The first is the element oxidized. The element oxidized is the element whose oxidation number or oxidation state becomes more positive as a result of the reaction. The element reduced is the opposite, meaning it's going to be the element whose oxidation state becomes more negative. It does not have to be negative, it just becomes more negative. As a result of the reaction. The easiest way to keep this straight, folks, is to think of a number line. When you're looking at the oxidation states, if it becomes more positive, then it is it's oxidized. And if it becomes more negative, then it is reduced. Additional definitions. The oxidizing agent or reactant is the reactant. Well, I'm going to write it slightly different because it'll hopefully be more visual. It's the reactant that causes oxidation. And basically, in order to cause oxidation, it means it contains the element reduced. Because oxidation and reduction have to go hand in hand. And as expected, we can talk about the reducing agent, reactant, which is going to be the reactant that causes reduction. And basically, in order to cause reduction, it means it's going to contain the element that is oxidized.
On the negative, on the number line.
Oh, okay, yes, you're correct. It becomes more negative, which should be reduced, yes. Come on. I'm having trouble with my equipment. Okay. Now that we have the definitions, we're gonna do some assigning. First thing we're gonna do is assign oxidation numbers. Or oxidation states. The second thing we're going to do is we're going to then apply that to reactions where we use the definitions to answer questions. Okay. There we go. Okay. So, sulfate, what is its formula? It's SO4 2-. We're going to follow the oxidation rules. Rule number 1 says elements in their standard state have an oxidation of 0. Folks, an element in its standard state is going to be a compound that consists of only one type of element, and that compound is neutral. An ion of an element is going to have the same charge as that element, as that ion. Hydrogen is going to be a +1. The only time it's not a +1 is if we're dealing with a hydride, which means that hydrogen is combined with a metal. Oxygen is going to be a -2. The only exception to that is if the oxygen is part of a peroxide, which I will tell you if it's part of a peroxide. And then we get into, so in other words, our oxygen here is a -2. The next thing says halogens. Halogens are a -1. Now it gives you 2 exceptions. Everything else you have to calculate. So we're going to have to calculate sulfur because sulfur was not listed in the oxidation rules. So we set up this equation very similar to how you set up an equation when you're trying to determine the charge on a metal whose charge varies. We have 1 sulfur times X. We have 4 oxygens times the -2. Now, the only difference is when we were dealing with ionic compounds, we were trying to make sure that the compound was charged neutral. You're not going to be worrying about that. Not if you got a polyatomic ion, that's fine. You're just going to set that equation equal to the charge on the ion. So X minus 8 is equal to -2. So X equals 6. So the oxidation state on our sulfur is a +6. Folks, once you determine the oxidation state of elements in a polyatomic ion, they're never going to change. So it doesn't matter where I go find sulfate. I could have sodium sulfate. I could have manganese sulfate. I could have silver sulfate. It doesn't matter where I find the sulfate. The sulfur is going to be a +6 and the oxygen is going to be a -2. So once you know the oxidation state for the elements in a polyatomic ion, you know them, period. You don't have to continue to calculate them every single time for multiple compounds. Let's look at another example. What if I give you just 10? Well, if you see this, that means we're dealing with an element in its standard state. So it's 0. If I give you Fe3+, the oxidation state is a +3. Because ions will have the same oxidation state as their charge. You may not have, but some people wonder why I write charges as 3+. Why I've always written the charge where the number came before the sign. We actually do that so that we can distinguish a charge from an oxidation state. So let's look at another example. Let's do sodium dichromate. Sodium dichromate is made up of sodium ion and dichromate ion. Now let's determine the oxidation state. Well, for sodium, since it's a single element in its ion form, its oxidation state is going to be the same as the charge. Now let's deal with the dichromate. To deal with the dichromate, we've got to continue following these rules. And the first rule we have that applies is oxygen. Oxygen is a -2. What you don't find is you don't find a rule for chromium. We don't know chromium, therefore. So we're going to have to develop an equation. 2 chromiums times X plus 7 oxygens times a -2, and we set that equal to its charge. Two X minus 14 is equal to a -2. 2X is equal to 12. So X is equal to 6. So this chromium hexavalent chromium. It is chromium 6. Questions about assigning oxidation states? You got to follow the rules. Okay. Well, we'll be doing some more of that, but we're going to do it with reactions. And then we're going to answer whether the element is oxidized, the element is reduced, who the oxidizing reactant is, and who the reducing reactant is. The reaction we're going to do is the first reaction you did in the laboratory. You reacted magnesium with hydrochloric acid. First of all, this is a single displacement reaction. How did I know it's going to be single displacement? Because I was dealing with an element and a compound. In a single displacement reaction, the element is going to replace the cation of the compound. Meaning magnesium is going to replace is going to replace hydrogen, leaving hydrogen by itself. Now, what charge does magnesium take when it's part of a compound? It's element 12. 2 plus. What charge does chlorine take when it's part of a compound? Element 17. -1. So what is the formula of the compound that is made? Now, hydrogen. What does hydrogen look like when it's all by its little lonesome in nature? H2. Those are the products for the reaction of magnesium with hydrochloric acid. You made magnesium chloride and hydrogen. Now, when you were performing the reaction, if you looked at it, the magnesium was a solid strip. It's black up there. The element magnesium is black, the letter is black. That means it's a solid up there. Blue means that it's a liquid up there. Red means that it's a gas. So since the magnesium, number 1, it was a strip of magnesium that you used in the laboratory, but number 2, if you're looking at it on an exam, you're like, okay, what state of matter is it? Look at the periodic table if it's all by itself. Hydrochloric acid, what is it? It's an acid. So what is its state of matter? Aqueous. Magnesium, now when you reacted the aqueous hydrochloric acid with the magnesium, what did you see? You saw bubbles. Bubbles means that somebody's a gas. So which one of those 2 compounds up there is likely the gas? Hydrogen. We could have known that because it's red on the periodic table. Magnesium chloride is an ionic compound. So what am I going to have to use to know the state of matter of magnesium chloride? Huh? I got to use my solubility rules. The rule for chloride says chlorides are soluble except for lead, silver, and mercury too. This isn't one of those. So this is soluble. Now I need to balance it. To balance this equation, you need 2 hydrochloric acids. Okay. I'm going to let you work through the complete ionic and net ionic on your own, but I do want to do this with respect to the oxidation rules. Rule number 1 says elements in their standard state are 0. Do I have any elements in their standard state? Magnesium, so it's going to have an oxidation number of 0. Do I have anything else in its standard state? Hydrogen, so its oxidation state is 0. Again, you're going to know that it's an element in its standard state because it will be a compound that consists of only one type of element, and that element will be neutral, or that compound will be neutral. Rule number 2 deals with ions. Do I have any ions in here? Maybe I should have done the complete ionic. Because magnesium is always the same charge. It's an ion. It's a +2. Rule number 3 says halogen is a +1. I mean, hydrogen is a +1. So this hydrogen in HCl is a +1. Rule number 4 says oxygen's a -2. Rule number 5 says halogens are a -1, and this does not fit the exception. Now what we're going to do is we're going to connect our elements. You will notice that magnesium goes from 0 to +2. Therefore, it is oxidized. You will notice that hydrogen goes from a +1 to a 0. Therefore, hydrogen is reduced. Now, you'll see this written as either reducing agent or reactant. I like the latter one because it tells me which side of the balanced chemical equation to look at. Because the reactants always appear on the left side of the equation. So in other words, we are going to be working with this side of the equation for these answers. Now, the reducing agent contains the element that was oxidized. Who was oxidized? Magnesium. What reactant was magnesium in? Magnesium. The oxidizing agent contains the element that was reduced. What element was reduced? Hydrogen. What reactant was hydrogen in? That is your answer.
For the oxidizing agent, like if it's, or for the oxidizing reactant, you don't put the coefficient.
You don't have to. Let's look at another example. One of the reactions that you did was iron. That was iron mesh, so it was a solid. And that was reacted with copper 2 sulfate. That was an aqueous blue solution. This is a single displacement reaction. We know it is a single displacement reaction because we started with an element and a compound. Being a single displacement reaction, it means that the element is going to replace the cation. So iron is going to replace copper in reacting with the sulfate. And then you have copper. Now, I'm just going to give this to you because of the fact that we're not looking at it, but because it was a pale yellow, it is a real pale yellow. That means that the iron is in its +2 oxidation state. And you notice that the iron mesh turned orangish, meaning that copper was plating out as a solid. So this is the balanced chemical equation for that particular reaction. Now we need to address oxidation states. Elements in their standard state are given an oxidation number of 0. Do we have any elements in their standard state? Iron and copper. Second thing, ions have the same oxidation number as their Ions have the same oxidation state as their charge. Do we have any ions? Typically, we're talking about the metals, folks. Do we have any cations? Who are our cations and what is their charge? Iron is what? +2. And copper is a +2. The next rule deals with hydrogen. We don't have any. The next rule deals with oxygen. Oxygen is a -2. Unless it's a peroxide. The next rule deals with halogens. Halogens are -1 unless they are one of the exceptions. Everything else you must calculate. But I already did this. What did I say about, we calculated sulfate earlier. It's a +6. Will it ever be anything but a +6 in a sulfate? No. Now, if I hadn't have done all that work earlier, then yes, I would have had to have calculated it. But now I'm going to connect the dots. My iron went from a 0 to a +2. So it was oxidized. The copper went from a +2 to 0. So it was reduced. Now we can get to the oxidizing agent. Or oxidizing reactant. Again, because we're dealing with the reactants, we're only going to be looking at the left-hand side of this equation. The element oxidized was iron. So what is it in? The oxidizing agent or the reducing agent? Remember, redox goes together. So if it's oxidized, that means that it is in the reducing agent because redox has to go together. So iron is in the reducing agent. The oxidizing agent, again, it has the element reduced is in the oxidizing agent. Redox has to go together. So where is the copper found? Copper 2 sulfate. Questions? Single displacement reactions and synthesis reactions are quite easy to figure out who's oxidized and who is reduced. Especially once you develop the net ionic equation. But redox reactions can get more complicated. I want you to be able to answer 4 questions. Again, it's going to be element reduced, element oxidized, reducing agent, and oxidizing agent. To be able to do so, you've got to be ready to assign oxidation states. Rule number 1. And folks, I keep going back to these rules. Rule number 1, elements in their standard state are 0. So the only element in its standard state is chlorine, because it's the only compound that consists of only one type of element, and that compound is neutral. Rule number 2, cations have the same, ions of elements have the same oxidation state as their charge. Potassium always has what charge in an ionic compound? +1. What charge does the manganese in manganese 2, oh, I just gave it away. In MnCl2 have? It's a +2, and we know that because chloride's a -1, and so it had to be a +2. The next rule says that hydrogens are a +1. The next rule says that oxygen's a -2. The next rule says that halogens are a -1. There are a couple of exceptions, but those exceptions don't apply here. So these halogens that I have not already pre-assigned are a -1. Everything else you got to calculate. So we need to determine what the oxidation state for manganese and potassium permanganate is. So I'm just going to do that. I'm going to drop down to do that one. KMNO4. We said that potassium was a +1, our oxygen's a -2, and we do not know our manganese. So we have 1 potassium times a +1. We have 1 manganese times X. We have 4 oxygens times the -2. And that is all set equal to 0 because the potassium permanganate was not charged. So +1 plus X -8 equals 0. X -7 equals 0. So X has to equal 7. So our manganese and potassium permanganate is a +7. It's in its heptavalent state. So this up here is a +7. Now we can answer questions by connecting things that undergo a change. Our manganese underwent a change. It went from a +7 to a -2. So, I mean, a +2, excuse me, a +7 to a +2. So it was reduced. If something is reduced, then something else got oxidized. In this case, it is chlorine. Chlorine went from a -1 to a 0. So it was oxidized. So the element reduced, we said, was manganese, and the element oxidized was chlorine. Redox. So manganese is in the agent that is the oxidizing agent. What is the oxidizing agent then? KMNO4. Again, redox. So the oxidizing agent is in the element oxidized is in the reducing agent. So who is the reducing agent? HCl. This last problem, though maybe not as complicated, is what it is more like what the oxidation will look like on an exam. The first two I did because it is part of your laboratory. Yes.
Will there ever be a time where there's like more than one element reduced or more than one element oxidized?
My experience, so the question was, will there ever be a time where more than one element gets reduced and more than one element gets oxidized? My experience is it is only a 1-to-1. Now, I will say there are times where the element oxidized and the element reduced are the same element. But in general, it always is a 1-to-1. Questions? Okay, I'm glad you asked that. When you are dealing with, for the redox reaction, I will not ask you to balance the equation. You don't have to balance redox reactions to get the information. Not yet. They will teach you how to balance redox reactions in college chemistry too. Other questions for me? Okay, then I will see you on Tuesday, but look for lots of stuff coming.
Like electrolysis, like stuff and stuff, is that's attached pretty much. I watched a video on that the other day.
Yep.
I was like,
That's what they're doing.
so I was like applying it as I was watching. Cool.
Your hair is so long.